Well, welcome to converting a monolithic application to a more domain-driven design. My name is Bill Penberthy, and I'm a .NET developer advocate with AWS. That means my job focus is really on working with .NET developers and helping them understand how to best take advantage of AWS services. We then kind of take the interaction and the feedback that we get from that, we take it back to our internal service teams, and we work with them to help them make sure that our .NET developer experience gets better. So also, there were some earlier sessions from yesterday where there's some overlap with the talk that I'm getting today. And I think if you look at all three of those together, they make an interesting story. Ann and Sarah, for example, did one on common quandaries implementing your first event-driven architecture. And Hassam did one on practical domain-driven design with EF Core. And I think both of those give additional insight into this subject. So if you missed them yesterday, I strongly suggest that you watch the recordings when they become available. So here's the agenda for the day. We're going to first spend a little bit of time defining domain-driven design, just to ensure that we're all on the same page. We'll then talk about some different technical approaches to doing the refactor, basically refactoring design patterns. After that, we're going to set the stage by talking about our fictional demo company and kind of describe the application that we're going to talk about converting. Then we'll go over how to plan and how to process through that refactoring. So we have a lot to do, so I'm going to just kind of jump right in there. Also, just wanted to let you know, the way that I have everything set up right now, I don't see the actual chat window for Slack, so I probably won't be all that quick at responding to any questions. So what is domain-driven design? They have whole conferences on it, and they've got organizations based to it. So it's actually a pretty complex subject. And I'm going to rip through it in about 6 minutes. So I'll probably end up creating more questions than I'll answer, but I at least want to get some of the language established that we're going to be using as we move forward. So what is domain-driven design? I've seen it referred to as a system design approach, which is basically the first bullet there. It's also referred to as a way of helping to understand priority because of its emphasis on building out the most important core areas first. Lastly, it's also considered a set of patterns for building enterprise applications. In my mind, it's kind of all three. It's a design paradigm that requires an as complete as possible understanding of the business, its life cycle, and how that applies to the system that we're managing. So there's 4 concepts that we're going to go over first: the domain, the model, the context, and the business and ubiquitous language. So the first is domain. The domain is the sphere of influence or activity, the subject area that drives the creation or refactoring of any applications that the business needs. Simply put, the domain is everything that your company does. This also means that no matter how similar different companies in the same industry may be, their domains may be slightly different. The next core concept is a model. This is a pretty simple definition. A model is the set of concepts that will be implemented in the software. A domain model then would be a set of concepts that define the domain that will be implemented in the software. But this is really different from how model often ends up being defined, which is basically as a class. This is especially prevalent when you think about frameworks like MVC or MVVM, where M equals model and is just kind of represented by a single class that you pass to a view. This model is much higher level. Instead, these class files, interfaces, and other code constructs all basically work together to define the model, the set of concepts that we're trying to implement. The next is context. So there's 2 levels of context. The first, simply context, is the setting around which terminology is defined. In this case, it's our domain. Every domain model lives in precisely one context, and a context contains precisely one domain model. The next level of context is a bounded context. A context becomes bounded when it's defined to the level of providing explicit boundaries around a set of models, sometimes called subdomain models. A lot of use of the word model there, isn't there? There could be multiple bounded contexts within a single context, just as there could be multiple subdomain models that exist within an overall domain model. So let's consider a retail sales company. One bounded context could be the consumer sales that they're doing. Another bounded context could be the system that manages the product inventory. A third could be the system that manages their orders and invoicing. All of these are sets of explicit boundaries around a set of specific subdomain models, and they identify and define the rules to which each of those subdomain models must adhere. These different bounded contexts then may need to communicate with each other. So the e-commerce system needs to get order information to the sales and order processing, and the inventory system must know about that as well because you want to update the availability of the product. This whole relationship is within the context, so we need to make sure that we use the same terminology across these bounded contexts. And that same terminology is the business or ubiquitous language. So when working in domain-driven design, we want to build a domain model that captures the problem domain of the systems being built. And we're going to express that understanding in code and other software artifacts. To help us do that, it's important that the domain experts and developers really consciously communicate using the concepts within the models. So this means that the domain experts don't really describe a new user story in terms of a field on a screen or a menu item. They instead talk about the underlying property or behavior that's required on a domain object. Similarly, the developers don't talk about new instance variables of a class or columns in a database table. They instead use this ubiquitous language. And this is critical because if an idea can't easily be expressed using the ubiquitous language, then it indicates a concept that's missing in the domain model. This means the team needs to work together to figure out what that missing concept is. Once this has been established, then the new field on the screen or the column in the database table follows on from that. It becomes clear what that should look like. The ubiquitous language already describes that relationship. So let's take a look at how some of these relationships work out. On the left, you have a team. I work at Amazon, so we would call that a two-pizza team. The team is made up of both domain experts, or the business, and the delivery team, which would be developers, DBAs, QA, PMs, and whatever roles you have for your organization. So this team works to create the shared language while working through their domain knowledge. The domain knowledge is distilled into the bounded contexts and described in terms of the ubiquitous language. Each of the bounded contexts has relationships with other bounded contexts, which are defined around the various subdomains that were identified through the ubiquitous language. So now that you know some of the words, let's look at some of the common implementation approaches that are recommended as part of domain-driven design. So these are some of the implementation recommendations that we're going to go over. Each of these you'll pretty much have heard as being common in domain-driven design. Microservices, messaging, eventual consistency, command query responsibility segregation or CQRS, and event sourcing. So microservices, there's really no single definition for microservices that I found. There are instead a set of defining characteristics, some of which I've listed on this slide. Like a microservice processes communications over a network using an agnostic protocols such as HTTP. Microservices are generally organized around business capabilities. Other descriptions of them is that they tend to be smaller and more limited in scope, message-enabled, part of a bounded context, independently deployed, and responsible for its own data. So I saw some definitions for microservice that I felt were a little bit confusing. So I wanted to point out that a microservice is not a layer within a monolithic application, for example, a web controller or the backend for front end. Rather, it's a self-contained piece of business functionality with clear interfaces and may, through its own internal components, implement its own layered architecture. But it's important to remember that domain-driven design does not require microservices. You can build an application that can be called monolithic through the use of domain-driven design practices. However, Microservices provide a relatively easy way to ensure that the bounded contexts stay distinct. Crossing those boundaries when using microservices requires a much greater intent than would be necessary if it was simply a monolith using an in-process namespace difference. And I want to go into a little bit more detail about the responsible for its own data, because this is one of the areas that I had the most difficult truly buying into. I was a SQL Server guy. Normalization to me serves a purpose. Allowing a microservice to be responsible for the data that it cares about was okay, that made sense. Until you realize that some other bounded context also cared about some of that data. And that they may both be storing that data separately, and perhaps with different data designs, because they care about different parts of that data. And even in different databases, and not just different databases like what you can do in SQL Server, but perhaps one of them is storing it in a NoSQL system while the other one is storing it in a relational database. But I came around, and we'll talk about this a bit more when we get to eventual consistency. So the next subject we're going to talk about is messaging. Messaging is a system and architectural approach that allows for communications between multiple interested parties. There are many different examples of messaging platforms, including RabbitMQ, Apache Kafka, and some of our various AWS products. There are different behavioral approaches, such as PubSub or message queues. But what they provide to domain-driven design cannot be overstated. First, a messaging system decouples providers from consumers. This means that a consumer does not have to know where to go to find information that they care about. They just need to be able to recognize that information kind of as it goes by so they could pull it out and act on it. The second is that the use of messaging provides simple horizontal scaling. If the machines that are handling messages are being overworked, you can simply add more. The next is platform and language integration. There's no need for the message sender and the message receiver to be written in the same language or running on the same operating system or using the same framework. They can be completely discrete and different operations. A messaging queue also provides reliable communications because it typically takes a store and forward approach where the message is stored in the queue and then forwarded to all of the subscribed listeners. So messaging is an ideal approach when needing to work with disconnected systems, especially that may not always have communications. Using a store and forward approach means that regardless of when the system connects to the network, they're able to catch up on all of the messages that they may have missed. And the last is that a messaging system automatically acts as a mediator. So with the mediator pattern, communication between bounded contexts is encapsulated within a mediator object. Those subdomains no longer communicate directly with each other, but instead communicate through the mediator. This reduces the dependencies between communicating systems and thereby reducing coupling. With this, if an application becomes disconnected from the others, it need only to reconnect to the messaging system, not all of the other messaging applications. And I've seen instances where a consumer could be listening to messages from a couple dozen systems. Imagine what it'd be like trying to connect to those each individually. So the next important concept when considering the implementation of domain-driven design is reliance on eventual consistency instead of strong consistency. Not every bounded context has to know everything about the models within the other bounded context at all times. Instead, they may simply need to know some of the things. If you look at the time graph on the slide, the column of green dots demonstrates strong consistency. So a system with a single shared database would have. All the data is stored in a single place, and so it becomes available to every other consumer of data at the same time. Once the save is committed, everyone knows about it. The only real lack of consistency between the customer and the product record would be the milliseconds of that database transaction. Eventual consistency is different. This is the staggered orangish dots. It means the data will be consistent eventually. There will be some time before all of the other systems understand that data. And that meaning of eventually is something that you consider when you architect out your systems. So eventual consistency is important for not only domain-driven design, but in my mind, in any effort that expects decoupling. It's because it provides the service the most control over itself. The first bullet here pretty much tells the main story. If strong consistency was required, i.e. two bounded contexts needed to know the same information at the same time, that means that either one of the bounded contexts has to know enough knowledge about the other so that it can go get that information from it, or they both access the same data store, kind of like what we talked about earlier. Doing that means that changes in one domain, such as to that table or to the service that the one microservice may have been calling to another, those all could impact the domain. So the next item is command query responsibility segregation. So this came around because of two driving forces, collaboration and staleness. Collaboration refers to those circumstances where multiple users will be using and modifying the same set of data. And that's whether or not the actual intention is that the users collaborate with each other. It's just the fact that they're sharing that same data pretty much at the same time. So there are often rules which indicate which user could perform which kind of modification, and modifications that may be acceptable in one case may not be acceptable in another. That's all collaboration. Staleness refers to the fact that in that collaborative environment, once data has been shown to a user, that same data may have been changed by another actor. So by default, it's stale. Almost any system which makes use of a cache, for example, is serving stale data, even though they're doing it for performance reasons. If the data we're going to be showing users is stale anyway, is it really necessary to go to the master database and get it from there? It seems like, since you'd be pulling it in, you'd be pulling out, you'd probably be mapping the domain object to a DTO object and then mapping it to a view model object. It seems like we're doing an unnecessary amount of work based on the assumption that reusing code that's already been written is easier than just solving the problem at hand. Instead, let's try a different approach. How about we create an additional data store whose data is a bit out of sync with the master repository? I mean, the data we're showing the user is stale anyway, so why not reflect that in the data store itself? So with that kind of a concept, command is an action taken that adds, edits, or deletes data from the primary data store. A query, on the other hand, pulls out a read-only snapshot of the data in either a primary or a secondary data store. And so in CQRS, basically you split the definition about what you're doing with that model into either a command, I'm going to add, edit, or delete it, or I just want to look at it, the query. So there's some benefits to using CQRS. These benefits include independent scaling, optimized data schema, separation of concern, and simpler queries. By separating these two, you allow them to be managed differently. You can scale each differently or use different schemas, such as more normalized data for reads. And that will tend to lead to simpler queries because if that's the approach you're taking, you're not going to have to worry about joins when you're doing your queries. So segregating the read and write sides can also result in models that are more maintainable and flexible. For example, generally most of the complex business logic goes into the write model. The read model can be relatively simple. But there's also some real challenges to CQRS. The first is it's complex. It may not be necessary. It's a lot of work to do CQRS, and many times it just may be overkill. Adding to that, it's important to remember that to define CQRS at a bounded context level rather than as a domain-wide implementation pattern. Not every bounded context will need CQRS. So allowing each bounded context to manage its own data read-write rules will provide the most flexibility going forward. And another challenge is updating schemas and data during a release, especially when the read and write are significantly different. Imagine you're doing a release and one of the things that you have to do is update the value of a status field. What does that mean in this kind of an approach? So all of these are worth evaluating if you're considering CQRS for a project. So event sourcing. According to Martin Fowler, the fundamental idea of event sourcing is that of, let me read it here, ensuring every change to the state of an application is captured in an event object and that these event objects are themselves stored in the sequence they were applied for the same lifetime as the application state itself. So basically, event sourcing is a process where all changes to application state are stored as a sequence of events. Now, this could really sound like a stinker because a typical application has a lot going on with it. However, you think about the other concepts that we've already talked about, such as messaging, eventual consistency, and CQRS, you'll see that there's the likelihood that many of these events are already being created for each bounded context. So implementation of storing these events is almost trivial because you're already doing it. Event sourcing provides several layers of information. The first is to really be able to identify at any point in time the state of any piece of data. The second is that you have recovery built in, restoring an old, well-known database, and then rerunning all of the messages that were played will put that data in that database into the proper stage. And since it's replaying it, you actually, if you design your eventing properly, have the ability to retroactively fix errors. So think about that for a moment. You know, with the current design, say, of a single monolithic database managing it, an error in business logic somewhere can lead to bad data. Say that we made a change in a product service where the request to change the product inventory because of a sale resulted in the inventory count being increased rather than decreased. That would be difficult to fix. With event sourcing, after you fix the business logic, you can restore the older database and rerun all of the events for that data. Since the business logic is fixed, the values will all be updated correctly so your data's been repaired. You know, yes, if there's a lot of events, it may take a while to do that process, but I can almost guarantee you that it'll be faster and more likely to be correct than trying to understand and fix those errors in some other way. So there are some requirements that event sourcing does a good job of fulfilling. The first is if you want to capture the intent of the data. An example of this would be, say, changes to a customer entity that are captured as a series of specific events, such as moved home or closed account or something like that. That kind of intent can also be captured along with all of the data changes. Another reason to use event sourcing is if you need to minimize the occurrence of conflicting updates. Event sourcing can help prevent concurrent updates from causing conflicts because it avoids the requirements to directly update objects in the data store. You know, however, the domain model really must still be designed so that it can protect itself from the requests that might result in an inconsistent state. The next reason, and one I think I actually mentioned last slide, is that if you're already using events within your system, you're already mostly there. You may need to tweak some of the events as well as add some additional events that you may not have been managing. But if the infrastructure is already there and being used, then your implementation path is already much simpler. And the last item I tossed on the list was if you want the flexibility to change data format. Changing the messaging schema is pretty simple, and interpreting the changes can be easier as well. You know, if none of these items are a concern for you, then using event sourcing is likely to add complexity for no gain. And that's one of the problems that I've seen when people that are looking to take a domain-driven design approach to building software is that they feel since they're doing that, they have to use all of the buzzwords that go along with it. They have to use CQRS. They have to use event sourcing. And that's not always true. Many times, what I've seen is by separating the bounded context and setting up eventual consistency, you find that a lot of the complexity that the original system had is no longer necessary because it was caused by poor boundaries between the concepts. That means that letting each microservice basically manage its own data through a CRUDly approach is fine, and CQRS is not necessary, or may only be necessary in one or two highly used and highly complex bounded contexts and not across the board. So we talked a little bit about DDD. Let's take a look at some of the refactor patterns that I've used when refactoring applications. These strategies, or refactor design patterns, are different ways in which you can change your system in your effort to build a domain-driven design. They're certainly not a complete list, but they offer different approaches for refactoring systems. These patterns are also not exclusive. You'll find that as you work through the changes, that you'll use many of these, if not all, sometimes together. So these patterns, and I'm sure that you've heard of some of these, if not all, are Strangler Fig, branch by abstraction, and parallel run. The most well-known of these refactor patterns is the Strangler Fig. Implementing this approach means that you will create a new system running parallel with your existing system. Over time, you end up moving responsibility and functionality from the current system over to the new system. The primary differentiator in the Strangler Fig is that it depends upon a call from the outside of the system that will eventually go to the new system. So the idea with the Strangler Fig is that you'll replace the old monolithic system with the new system, one piece at a time, just as kind of shown as by the image on the screen. As you can see, however, there's one very big requirement for the Strangler Fig pattern to be successful. That's that you have to have the ability to clearly map the inbound functionality that you want to refactor. If your code being migrated is deeper, or there are existing calls coming to it from both inside and outside of your application, then the Strangler Fig is probably not your best approach. Instead, evaluate the branch by abstraction pattern. This is very similar to the Strangler Fig pattern. However, the Strangler Fig pattern depends upon external calls coming into the system, while the branch by abstraction approach works completely within your system and does not require any changes to the systems outside the application being refactored. I've seen where a lot of people kind of combine both of these patterns and architectural approaches and call it the Strangler pattern or sometimes the Strangler Fig pattern. But they're really uniquely different approaches to solving complex refactorings. And I think it's important to delineate between the two because of the different implications they have as to how you're going to implement them. In the branch by abstraction, you determine what functionality is going to be removed and then build an abstraction for it. You slide that abstraction into the code and ensure that all your consuming code is basically calling that abstraction. Once you've made sure that all of that code is calling the abstraction, you can start replacing that initial implementation with the new one. So I've seen this approach used multiple times, most commonly when implementing a repository for data persistence. So by abstracting out all the crudely calls, you can switch in and out databases or even persist through REST services instead. So the next pattern is parallel run. So Strangler Fig and branch by abstraction basically allow old and new code to coexist in production at the same time. However, you generally only run one path at a time. Generally, there'd be a switch somewhere, say in the configuration or even in the database, that tells the system to use either the new or old branches of the code. If the new branch breaks, you switch back to the old one, and everything should just be running like it was before. Parallel run takes this a bit different, in that it runs through both the old and the new code at the same time and then compares the results. I mean, it sounds a little crazy, but consider the situation where your current state is a big old monolith and you want to move to microservices. And in traditional domain-driven design, you want each microservice or bounded context to be responsible for its own data management. This means that you'll be implementing both new business logic as well as database design, implementing new database systems. Parallel run would be a really good way to test the system. Let the system you know works, do the heavy lifting, but completely exercise the new system as if it's also doing the work, and then compare the results. Your comparison engine could be as simple as a SQL script to compare data, or it could be as complex as a fully running service that's listening to database calls and event queues and comparing them to what the expected results are. Whatever makes the most sense based off of the changes you've made, your internal systems, and the kind of architectural approaches that you're taking. The last time I used this approach, we were able to find a whole lot of edge cases that were missing when building the application. Some of those edge cases we missed by design, but there were a lot more that we had missed coincidentally that no one had ever thought about the details involved in that edge case. Also, we found several instances where the current system or the previously running system was actually doing work incorrectly. It's just that no one had noticed it yet. So there are 3 additional design patterns that I tend to go over in the full day session of this, but simply don't have the time now. The first is UI composition. This is an implementation approach that takes advantage of the various UI implementation patterns such as MVP, MVC, MVVM, so that new functionality is added or replaced by splitting the calls at the UI level and splicing the results back into the data being presented in the UI. Basically, you split out the data from the new service that's being deployed, and in your management framework, such as the controller and MVC, you call the new service and stitch that data back into the data being presented back to the UI. This can happen with new information using a new design-driven or a domain-driven design service, or existing information that's being refactored somehow into a different area. The next pattern is the change data capture approach, in which we listen to and react to changes in the data. This is generally a transitive pattern, i.e. it's something that you kind of implement for a while during your conversion, but it can also become part of your strategic move to a more domain-driven design approach. Especially in systems where there are more than one application that listens to various data tables, and some of those may be ones that you don't have any control over, like installed apps. So many database systems give you the ability to be notified when a data table is changed. You use this notification to perform additional work. For example, in one system I worked on, we used SQL Server to notify a process that would then take the data that had changed and queue up a message in the messaging system that we were using. And the last design pattern is the decorating collaborator approach. This approach uses the decorator design pattern to take advantage of the results of the code. So if any of you have written an HTTP handler for IIS, then you've implemented a type of decorating collaborator, especially if you've done it on the HTTP result rather than the HTTP request. If you're not running IIS, then this would normally be done by creating a proxy between the caller and the code. Then that proxy would be responsible for calling the collaborator with the results from the response. So we've talked a little bit about DDD and some of the patterns to think about as you're doing Refactor. Let's kind of set the stage for the demo app that we're going to walk through. This is important because you need to get some of that ubiquitous language for these conversations. So our company is an e-commerce company that sells widgets. These widgets can come in different sizes, colors. It can be provided by multiple manufacturers. There are several different sales approaches taken by the business. For example, the business sells directly to consumers through the forward-facing section of the website. The company also sells through joint marketplaces like Amazon and a couple other through APIs that are managed within the inventory module of the system. The company also acts as a distributor to other retailers where we provide quantities of product at discounted prices through a B2B marketplace, basically, case quantities at a wholesale discount. There are multiple other modules. There's a purchasing module that the purchasing and receiving department uses to manage purchase orders, define the inventory that's received, and account for incoming product. There's a module built for order fulfillment that handles things like pick lists and the capture of the shipping information. There's a module that's only used 3 to 4 times a year by the warehouse staff to audit inventory. There's even a module for the customer service staff that they use to manage customer interactions. Whether they're purchases, returns, billing issues, problems, anything like that. Now, this may seem like a lot of things going on because we've pretty much talked at least 7 different business areas so far. However, it's pretty normal. You'll see this kind of evolution through systems as companies grow. They'll start off with a smaller system, they'll add in a new module, they'll add in another module, and that's kind of how you get these monolithic approaches over time. Another similar approach to this is where rather than building multiple modules within a single monolithic application, so in this case, one big website, companies can take approaches where they build different systems for each. So rather than having one big system, you have a whole bunch of medium-sized systems. We're not going to talk about that because that tends to take a slightly different approach to refactoring because of just the way that you have to manage prioritization. So with what we talked about, a rough system diagram kind of looks like this. There's a centralized data store that stores all of the transactional data across all of these systems. There's a layer of web services that handle all of the work necessary within that area. And note, I didn't say domain, though I may have in a more casual conversation. That's just because I'm trying to reserve that word for this whole this whole thing that we're going through right now. And there's also a lot more services than these, of course. This is just some of the more obvious ones. On the right-hand side is a bunch of servers, which kind of represents the load balanced big old web app. And if we look at some of the communications that are going on within these services, it starts to look like this. So yes, the big old web app calls a lot of these different services, but there's also a large amount of service-to-service calling going on as well. So imagine how scary it could be to try to figure out how to add some new functionality into the purchasing module in the big old web app. How do you wedge that in amongst some of the other rules? With the current design approach, anything you do for one module can potentially affect other modules. What this diagram also shows is how business rules tend to get scattered amongst different areas of the system. In this case, there's some orchestration going on in the big old web app as it determines what services to call when and with what information, as well as all of the intercommunications going on within the services. You know, there's more likely decisions being made in the big old web app around processing the order. And if the orchestration or management is not done in the big old web app, then it's most likely done in some other service, which accounts for all of this other communication that's going on inter-service. So is that the best way to do this? Probably not. So let's continue and let's take a quick look at the database design. The slide shows a list of some of the tables on the left. Sorry, I'm so used to standing in front of the presentation, it kind of threw me off there. So a list of some of the tables on the left and a partial rendition of the database diagram on the right. What does this show? Well, first, that there's a single database that contains all of the information for the company. Second, I'd like to say that there's at least some separation of concern because at least there's different schemas like orders, purchasing, products, and website. See that little yellow box there? That's the most used table in the system, the users table. It has lots of foreign key references to it because of the created by column that is present in a lot of the tables, but not all of them. However, there's also some relationships that don't have foreign key definitions. Let's look closer at the orders and order details area, the three tables that are in the green there. The order details only has one foreign key in it, and that's to the orders table. There are no foreign keys to the product table, or the size table, or the color table, or any of the other tables where you may expect to have relationships. The reasons for this decision is lost in time, but it probably had something to do with some refactor or redesign somewhere along the way, which meant that historical orders would not be able to support the foreign key relationship, so it just simply wasn't added. And there's all sorts of these little code smells throughout the application. And to be honest, probably in every long-standing application that I've ever worked on. So we shouldn't judge this one too harshly. So there are really two serial processes going on. This slide shows the order in which they go and what service has the responsibility of running them. The first is on the website as it builds out the required information, namely the user, customer, and payment, and then sends that to the order service. The website then empties out the shopping cart. Once the call gets to the order service, it turns around and calls the product service to update the inventory, calls the communication service to send order confirmation email, and somewhere along the way, it's doing its own processing as well. So to support those 7 steps in the order flow, the communication flow looks something like this. Other business flows are very similar. Everything that's going on in the big web application talks to other services, and then those services talk amongst themselves as they try to get the appropriate information that they need to build out their own requirements. In some of them, the website does some orchestration and then hands it off to the service. The service persists it somehow and then performs additional processing based off of whatever additional business rules were defined for that service. So this is all what we're going to refactor. So how do we even start to fix this? First, let's define the rules that we're going to work under. The first, and this rule should be very obvious, is to take a very incremental approach. Do not try and deliver everything at once. In fact, incrementing both horizontally and vertically is okay. The most important consideration is that you make continuous progress. The next rule, and probably even more obvious than the last, is that you must continue to support the old ways of doing things. Since there's so much interaction between services, it's likely that there will be other things going on that are either missed, unknown, or you just haven't had a chance to get to yet. Next is to make smart technology decisions as you go through the process. I know some of you are kind of looking at me about that, but I've seen a tendency to look small when looking at these technology decisions. Quotes like, just enough to get by, or I'll add that later, they end up leaving you with as much tech debt as you already have now. Remember to plan for tomorrow's work, next quarter's work, and next year's work, and make the best technology decision as possible. This doesn't mean that all of these decisions have to be implemented now, however. What this means is they need to be accounted and planned for. It's perfectly okay to say, I want to move this order service away from SQL Server to a NoSQL database because I figure that'll more easily support the future changes that the business sees, and not do that work until you want to make those future changes. But make the decision as early as possible and make your design and architectural decisions around that end goal and how you plan to get there. That's going to help you understand which of those domain-driven design patterns that we talked about, CQRS or all that, how they're going to fit in with your overall system. The next is don't be afraid to change the way things are done. That you historically perhaps did all of your data access through stored procedures doesn't mean that you have to do that moving forward. Instead, take the time to evaluate your current implementation approach against your end goal. Some of what you have done can just be picked up and moved. Other existing approaches may simply need to be scrapped and redone. You should never put yourself into a place where that's how we have always done it becomes an acceptable answer. Lastly, and I'm harping on it again, but build that ubiquitous language cooperatively across all of the teams. Agree on the language and stick to it. Change the language as needed, but do it together. Even if everything else turns into a big old smelly bag of nope, having the language in itself will make the whole effort seem more worthwhile, even if the only time that you're using it is to yell at each other in the retrospective meetings. At least you'll be speaking the same language. So I would keep these rules in the back of your mind as you start determining strategies for your refactor. So one of the easiest ways to start building your ubiquitous language is to build your context in bounded contexts. In this case, we're going to define the context as the website and its supporting functionality. So for this company, everything. The bounded contexts then become the different business areas or domains or subdomains. Many of you probably have considered the phrase domains and subdomains before, so remember that a bounded context is the same as a subdomain. In this case, we have listed product, customer, purchasing, order, and geography. Well, there are many, many others. When you evaluate your own context, I would recommend that you stay away from reinforcing the constructs that your system already has built into it. Step back and actually evaluate what's going on within in the domain and the context. Remember, one of the key points for this is building your ubiquitous language. Define and describe what needs to go on to support the business, and don't be afraid to redefine terminology as you go through it. In many ways, this may make it easier. Let's say you currently have a quote service that performs a series of actions. If you determine that the things that service cares about is correct, then perhaps you can call it a quote in the new system because it implies the same responsibilities. If, however, you need to change the behavior, I recommend that you rename your ubiquitous language to something new, maybe estimate or something else that describes the new set of behaviors and responsibilities. You know, this is especially important because almost by definition, a monolithic application has had some domain creep. An example, say your quote knows what order number that it was used for. Now is your time to fix this. You'll see that even visualizing using a bounded context approach is a different way to look at your business. It seems less rigid. It also makes you look at the responsibilities of the bounded context as a whole and not necessarily as part of a distributed system. Once you have some ideas around your bounded contexts, the next thing is to define the communication between the different bounded contexts. With the subset shown on the slide, we know that the purchasing bounded context has to get information from the product bounded context. And I got to stop saying bounded context because it's just killing me. So the customer gets information from the order and geography. Order gets information from customer and product. Why? Because it makes sense. They have a relationship between them. What does purchasing do if it doesn't relate to products? Or what are orders without products? So as you build out these communication streams, pay attention to the three important details about the communications. What each of the contexts needs to know, why they need to know it, and when they need to know it. Because understanding those key bits will help us design out our system. So I pulled out the communications between product and purchasing. I use this as the example because of how it shows how domains can be different for different companies. The way that this company defined their business is that the product is the most important thing. And then they will find out the best place to buy the product, to purchase it. Many other companies that I've worked with have a different approach, where the purchasing domain actually provides the product to the product's domain. So the purchasing domain is actually responsible for creating the product and then providing that to the product domain. This one is different. It takes the other approach. The product bounded context is responsible for creating the product and then allowing that to be sold through the purchasing bound context. So in this particular case, the product bounded context kind of just lets the purchase bounding context by sending this pieces of information in the message. So here's how this relationship in the current system is currently defined in the database. The half with the color is the purchasing schema. The right side is the product schema. There's just a single foreign key relationship from the purchase order details table in the purchasing schema to the product table in the product schema. If you take a look at the product table, you'll see that it has 3 tables directly related to it, with a couple of those related to other tables. This means that a fully instantiated object graph of a product is going to be pretty gnarly. And it's hard to imagine that the purchasing system needs all of that information. And it doesn't. So while it needs a few more pieces of information than what we showed here, it's only a small fraction of the overall object graph. Basically so that the purchasing agent can fill out the purchasing order. But it's been identified. That's what the context needs, and that's why it needs it. The last question is when. In this case, does a purchasing context need strong consistency or does eventual consistency work? What kind of lag can your system tolerate between when the product context knows about when a new or changed product happens and when the purchasing context knows about it? The more tolerance you have, the more eventual consistency is appropriate. So back to how to plan your refactor. So we talked about describing context and defining communications, what, why, and when. The next step is determining the most critical core area of your application and define it in detail. If you remember back to the earlier slide on DDD, it used the phrase, a way of focusing on core areas for design consideration and emphasis. That's what we do now, determine those core areas. Some of this will be at the infrastructure level, such as defining, sending, and receiving messages. Others will be more domain level. As you go into your refactor, there are a couple of items you have to do as part of your planning process. The first and most important is to define your critical area. This most likely will include several bounded contexts. This could also be spread across multiple systems. And once you've identified those critical areas, define the communications between each part, and then start breaking that chain of dependencies. Remember this process? And the communication schema that looked like this? Would an approach like this make more sense? Assuming that eventual consistency is okay with the business need, this could mean solving this problem. The user website places an order. The website bounded context says relevant information about that order. It then sends an order placed message. Orders and products are both listening for order placed messages. The order takes that message, saves all of the information locally, and does whatever other business activities need to happen. The product also takes that message, but since all it really cares about is the product ID and quantity that was ordered, it just takes those pieces of information and decrements the quantity of available product. And if evolution of the business means that some other domain is identified and added to the ubiquitous language that cares about an order being placed, then you just add that in as well. And you don't affect any of the already existing code. None of that has to be changed, so rolling in that new functionality is pretty much as low risk as you can get. Unlike what you would have to do if you're going to make that change in the current version, say adding in a new step into the process that the web has to perform. And since the change is happening on the website, it has the potential of affecting all of the other steps of the process that are happening on the website. So the risk of that change is much higher than using the new design. So we know that the website calls multiple services as part of its processing, such as the order, user, and payment. So let's talk about those two highlighted systems and how they should change. So this is what our goal system looks like. The website will pass information along to the website service. The website service will persist that information that the website thinks is irrelevant and then queue up a message containing that data. The order service, rather than being directly called by the big old web app, is now listening to the message queue for messages that fit the appropriate criteria. So we're adding two new constructs here. The website service and its attached storage, in this case, Amazon Aurora, and the message queue. We're changing the big old web application by removing all of the business process that it was doing and moving that into that processing into the website service. We're changing the order service so that it listens to the message queue for order created messages. So the work that needs to be done, refactor the website to remove business process, create the new website service to do website domain work, and refactor order service to listen to message queue. So this is pretty much what the website looks now. There's a bunch of client-side logic in that hippie language JavaScript. There's a controller layer that accepts the user input and returns the UI elements. And there's a business logic layer that does all of the processing and orchestration. That's what we're going to move. So ideally, a lot of this would be easy to move because we already have an abstraction layer between the controller and the business logic. I don't know if I would necessarily call it a repository, but there's some kind of interface layer, a service layer, or something like that. If you do, then it's pretty easy to replace the current implementation with a layer that calls the website where this business logic will move to. If there isn't, however, we did go over a refactor pattern that would help with that. The branch by abstraction. In this case, you would add the abstraction layer between the controllers and the business logic, assuming that it's not already there. Once you get that done and can verify that all of the communications between the controller and the business logic are passing through that abstraction layer, you can then refactor the previous business layer to instead call the new website service. So right about now, you may be questioning my decision to create a new website service. So this is one of the most common decisions that people make, and I would argue incorrectly, is to perform any kind of business logic in the website system itself. Instead, add a new layer of abstraction to the whole kit and caboodle, and use that as your first step for this reprocessing and refactoring, and that especially because this provides scaling. If business logic processing is expensive and the UI rendering is not, then you can scale them differently. You're already starting to get some gains for your separation. And it'll also decrease your risk of changes to the system as you move forward by decoupling the presentation and the business logic even further than you would in a traditional MVC approach. Each can grow and be managed on their own. So this is a higher level view of the current order service. It's pretty straightforward. There's the defined API that includes the endpoints called from the website, the business logic, and the persistence layer. When you consider this design, what kind of changes do you envision that would have to make for it? So let's take a look at one approach that you could do to make that work. So this is what an idea of what the order service would need to look like afterwards. First, we need to add a message handler. So this is going to pay attention to the message queue and react to the order created messages that come through and whatever other messages we end up caring about. Conceptually, you wouldn't have to change the API at all. That the endpoints for creating the order still exist are okay. Especially if there's other systems that may be calling that endpoint. That's not something that's happening in our case here because of the big monolithic app. But in one of those systems where there may be multiple applications that are doing it, you could just keep that API there until you've had a chance to refactor those other systems. We'll also need to add a messaging layer to process any outbound messages if we're going to be setting anything. And then we would need to refactor the business logic layer. So if we remember this approach, you'll see that the order service did the processing to update the product inventory and to send the order confirmation email. But it doesn't have to do that because those services will already know about them, because they're smart that way, because you made the same types of changes to them. This work seems intimidating. There's a lot of changes to go through. It'll be frustrating. It'll take you way longer than you expect. However, it's doable. I've done this several times myself. And as long as you concentrate on understanding your domain, building your ubiquitous language, differentiating your bounded contexts become clear, and in my mind, that's the hardest part. Defining the communication between these bounded contexts, as well as the business rules, within the bounded context, helps you understand the appropriateness of specific implementation approaches such as CQRS, messaging, and eventual consistency within each individual bounded context. After understanding all of that, it really seems that writing the code is simply an implementation detail. I know we tried to cover a lot of things in a short period. I appreciate you sticking with me, especially since we couldn't get as deep into the weeds as I imagine some of you were hoping. Some of those earlier talks that I mentioned to did go a little bit deeper. So once again, I say I recommend go take a look at those. So thank you. And don't forget to come over to the AWS booth. And if you haven't already registered for the drawing for a Star Wars Lego, come and do it. Thank you.